In this part, we will look at how to derive an overall rate law based on the rate limiting given. The most important part that we should have the mechanism of reaction. So I will show you the first example for one reactant reaction and the mechanism of reaction. Based on the mechanism of reaction here, for one reactant to produce one product, the first step of reaction is adsorption step. So the adsorption of A that attached with active site S will produce A dot S. So the first step is adsorption step. And then the second step, A dot S will react to produce B dot S. B is the product based on the rate equation given, which is A to produce B. So the second step is surface reaction. Okay, then the last step, the product B dot S reacted to produce B plus S. So when B detached from the active site, we call it as a desorption step. And if we look at the surface reaction, the reaction involve a single site mechanism for reversible surface reaction because it's only required one active site to produce the product. So you can write here reversible reaction, reversible surface reaction, and single site mechanism. So this is the clue on how we can derive the overall rate law equation later. Okay, first step, write the rate law for each steps of reaction. Alright, this is the rate law for each steps of reaction. Remember, for the species that not attached to the active site, we write it in terms of partial pressure. If the reaction is if the reactant in gas phase and the product in gas phase. But if the reaction is in liquid phase, we write it in terms of concentration. So if the reactant A and product B in liquid phase, we just replace the partial pressure. For example, for adsorption rate reaction, RAD equal to Ka Ca Cv minus Ca dot S per Ka if the reaction is in liquid phase. But now we assume the reaction is in gas phase. So I write it in the stoichiometric reaction equation. So the reaction is in gas phase. So all the species that not attached with the active site, we write it in terms of partial pressure. So this is the rate law for each steps of reaction. Now we want to determine which one is rate limiting. Okay, usually the rate limiting will be given, but for this example is just a general example. I will show you for the rate limiting. If adsorption is rate limiting, what will the overall rate law equation will look like? And then similar for if a surface reaction is rate limiting, how the overall rate law will look like, and also for desorption. So each rate limiting will give different overall rate law equation. So I will show it you one by one how we are going to write the overall rate law equation for different rate limiting, and why we need to write the rate law for each step. So all this equation 1, 2, 3, we will use it later after we determine which step will limit the reaction. Okay, first we look at the rate limiting if adsorption is rate limiting. Okay. Therefore, the overall rate negative R prime nearly equal to rate of adsorption. Okay, why this happen? This is because, remember, when adsorption is rate limiting, rate constant for the absorption step is much smaller than rate constant of surface reaction and rate constant of desorption. So therefore, because the rate constant is too small, that's why it will limit the reaction. So the overall reaction is depends on the adsorption step. That's the definition of adsorption rate limiting. Okay, now when adsorption is rate limiting, we need to solve the surface reaction and desorption reaction equation. Okay, so how we are going to solve it? So we need to consider at equilibrium condition. So at equilibrium, okay, from equation 2 and from equation 3. So at equilibrium, Rs will equal to 0. Okay, then the term, so when Rs equation from equation 2, okay, from equation 2 in previous page, right? So when Rs equal to 0, automatically term Ks also equal to 0. And then the term in the bracket, Ca dot S minus Cb dot S per Ks also equal to 0. Then rearrange for Ca dot S, so it will equal to Cb dot S per Ks. So we write it, we write this equation as equation 4. Okay, then next step, we solve for desorption equation from equation 3 at equilibrium. Rd equal to 0. Therefore, Kd also equal to 0. Then the term in the bracket also equal to 0. So Cb dot S equal to Cb dot S, Cb minus Kb Pb Cv equal to 0. Then rearrange for Cb dot S. Cb dot S equal to Kb Pb Cv. Right. So we label it as equation 5. Okay. Why? Kenapa kita kena cari term that attach to the active site? Why we need to determine the equation for the concentration of species on the active site? Because later in overall rate law equation, we need to eliminate the unmeasured variable. So remember in the lecture slide, I told you that we need to remove all the term that cannot be measurable. So that's why kita derive the equation for the concentration of species that attach to the active site, because we want to eliminate it later. Similar for Pv. Term Pv, we will replace it in terms of site balance equation. Right. So when we have all these equation, next step, okay, if you look at equation 4 ada two terms, which is Ca dot S and Cb dot S. from equation 5, we can replace CBS in equation 4 with equation 5. So next step, insert equation 5 into 4. So equation 4 will yield CA dot S equal to KB. So, yang ni saya tertinggal S. Okay, KS sebenarnya. KB per KS. PB CV. So, this is equation 6. Okay. Next step, we need to write the side balance equation. Okay, side balance CT equal to CV plus how many species that attach to the active site. So only species A and species B. So CT plus CA dot S plus CB dot S. Okay, then insert equation 5 and 6 into the side balance. So insert equation 5 and 6 into side balance. Right. So CT equal to CV plus KB per KS PB CV plus KB PB CV. Right. Then simplify the equation. CV 1 plus KB per KS PB plus KB PB. Right. Then rearrange for CV. Rearrange for CV. Why? Because later we want to eliminate CV. Okay, term CV. So, rearrange CV equal to CT divide with 1 plus KB per KS PB plus KB PB. Or you can simplify it as 1 plus KB PB bracket 1 per KS plus 1. Okay, so denominator dia panjang. So quite complex lah. The denominator of equation. Right. So when we have the CV equation, we already determine the equation for the species that attach to the active site. Now we can write the overall rate law equation. So overall rate law negative R prime equal to RAD, which is rate of rate of adsorption. So tadi yang equation CV, we can label it as equation 8. Okay. So what is RAD? So RAD equal to KA from rate law equation for each step tadi. So we write it back, PACV minus CA dot S per KA. So insert equation 6. Okay, insert equation 6 and equation 8 into RAD equation. So, kita insert one by one. KA, PA, CV ni kita replace later. Insert CA dot S dulu. CA dot S as what is the equation? CA dot S is KB per KS PB CV. Alright. Okay, then baru kita faktorkan KA PA minus KB per KS PB, then bawa keluar CV. So, in previous equation, saya tertinggal KA. Right, KA. KA. So, kena ada KA tu. Okay, then baru kita move to overall rate. Okay, so, okay. Then, finally, insert CV. So, RAD equal to KA PA. Bila kita bawa keluar CV, so PA minus KB per KA KS PB kena check one by one. Kena check one by one kalau ada yang tertinggal. Okay. Sebab the equation is too long. So, KA, KB per KA, KS, PB, and then multiply with CV. CV equation is CT per 1 plus KB PB 1 per KS plus 1. So, you check one by one the equation. Kalau ada yang tertinggal, term yang tertinggal. So, you kena be careful when we write, when we derive the equation. So, this is the final equation, the overall rate law. So, overall rate law, so RAD equal to negative R. Overall rate law equation when the reaction is adsorption limiting. When adsorption rate is limiting the overall rate reaction. Okay, ini baru derivation for one equation, one limiting equation. Then for if surface reaction limited, if desorption rate limited, same step, then I will show it in the next video.